Hi, in this video, we want to take a look at t-tests. Okay, so the goal of a t-test is to reach a conclusion regarding a population average. Okay, so remember, whenever we're doing statistics, whenever we're working with data, we don't actually know what's going on. I just have some observations to make an inference about. Okay, so what I'm interested in right now is the population average of where my data is coming from. Okay, so remember, data is always an incomplete representation of the population I'm interested in. So I want to know about the overall average of the population, and I have some data to do this with. Okay, so we're interested in the population average. All right, that's going to be a numeric value, and we're going to use this hypothesis testing framework to reach a conclusion. Okay, so hypothesis testing, remember, we break it down into two possibilities. Now, one of the two possibilities is going to, if it's correct, and I make a mistake and go the other possibility, then that has a heavier penalty. The other thing, other hypothesis, it has, it could be correct, and I could make a mistake and go with the other one. So remember, there's always two ways to make a mistake. What we're going to do is we are going to set the situation up that the null hypothesis is the one that if it is correct and I make a mistake, that is the worst case scenario. The alternative, if it is correct and I make a mistake and go with the other one, then, I mean, it's not good, but that isn't as bad as the other mistake. So, there's two ways to make a mistake, and we want the null hypothesis to be kind of like the situation where if it's correct and I make a mistake and go with the alternative, that is the worst outcome possible. All right, why do we do this? Whenever we're doing hypothesis testing, or in the vast majority of cases when we're doing hypothesis testing, we cannot control the risk of both of those types of errors. Mathematically, it's just kind of like a quirk. There are situations where we can control both, but we're not talking about that here. Okay, so what I'm going to do, I'm going to set it up so that I'm going to stack the deck so that I don't get the more severe error unless so I'm going to set it up so I'm just unlikely to make that severe mistake. Okay, so everything that we do in hypothesis testing really builds up around avoiding that type of mistake. So we call that a type 1 error. All right, so type 1 error, the null hypothesis is correct, but I go with the alternative. Everything about hypothesis testing is to avoid that one mistake. Okay, so let's go ahead and dig into this and let's proceed. Now, I'm going to go over the steps in hypothesis testing. Every single textbook does this a little bit differently. They might change the order of this, but I feel like this is a good way for someone to actually sit down and execute it. You'll notice that I actually went through and ran through every single step of this using the document here. All right, so the first step is identify the hypotheses in your test. Identify your null and your alternative. Identify the distribution for testing. This is going to be the boundary distribution. I'm going to, by hand, draw the distribution. Okay, this is a very important step to getting this right and understanding your results and getting the correct interpretation. I'm going to shade the region that corresponds to the alternative hypothesis. I'm going to establish what is my type 1 error risk tolerance. So how much risk am I willing to take on a type 1 error? Then I collect my data. So I want to point out right here, right now, everything here I do before I even have data. So when I do hypothesis testing, I have a game plan, I set everything up, then I get data, then I do the computations, and I reach a conclusion. After I have my data, I compute my test statistic. I find the cutoff of the rejection region. I'm going to compare my test statistic to the cutoff. I'm going to state my conclusion in terms of hypothesis testing. And then I state my conclusion in plain English. Okay. So now, if I'm presenting to, to most people in the world, that last part is the most important aspect. And I don't need to present all the stuff before it, but I need to have it ready to be able to defend it. the more technical of an audience I have, the more components of this test I need to present when I'm presenting my results. All right, so let's go ahead and do an example of a one-sided t-test. And here we're going to have the alternative on the left-hand side. Okay, so the left-hand side, when I say that, I'm saying that the alternative has the population average on the left of the benchmark value. All right, so here, like my benchmark aspect is 0. I just picked that number because it's an easy reference point to start with, but potentially it could be any value at all. So my alternative hypothesis is that the population average is greater than or equal to 0. My alternative is that the population average is strictly less than 0. All right, so now we believe that our data is coming from a normal distribution. This is important because we need a distribution to figure out probability values. All right, so what we're going to do, if I see strong evidence for the alternative hypothesis, I'm going to go with the alternative. If I don't see strong evidence for the alternative, I don't go with the alternative. Okay, so if I see weak evidence for the alternative, I go with the null. If I see neutral evidence, I go with the null. If I see strong evidence for the null, I go with the null. You'll see that most of the situations I'm listing, we go with the null hypothesis. The reason for this is because of the severity of the errors when we sat down and considered the ramifications of making a mistake. Okay, so remember, if I have extreme strong evidence for the alternative, I go with the alternative. All other situations, I go with a null. Okay, and because of this lopsided decision-making aspect, this is why we frequently refer to the null hypothesis as like the default hypothesis. All right, so now what is extreme evidence? What evidence is strong enough to go with the alternative? Well, that is truly a subjective decision. So what we're going to have to do is consider the situation, consider how much of a risk we're willing to take on a type 1 error, and then proceed from there. All right, we need to identify what the distribution is for our hypothesis testing. Okay, so what we're going to do, I'm always worried about the situation where the null is correct, but I go the other way. All right, so if mu is greater than or equal to 0 as the null hypothesis, well, what situation would I be the most likely to go with the alternative? If I control the risk in the situation where, like the worst case scenario, then if I have control of that risk, then I have control over all possible risk. So what I'm going to do, I'm going to look at the boundary case here. So I'll scroll up a bit. I look at the boundary of mu on these two inequalities. And I can see that mu equal to 0 is like that boundary cutoff. All right, so if mu is equal to 0, that's when I am that's the scenario in this collection of population averages where I'm most likely to make that error. All right, so I'm going to control the error there, and that way I know in all other possibilities I have at least that much control over the situation. And so remember, I'm picking the boundary distribution. So for us, mu is equal to 0. Now, the next step, I'm going to draw the distribution. This is super, super important to make sure you understand the output you get in a moment. Do this by hand. Okay, what I'm going to do, I'm going to draw the probability distribution I'm going to use, and I'm just going to shade the region that is going to be my rejection region. Why do I do this? There's a lot of components going on in this. I need to have some kind of like representation to remind me, like this is your decision. Okay, so my alternative hypothesis is that the population is strictly less than 0. So I'm looking for an extreme value on the left of the normal curve, on the left of the x-axis, to give me an extreme value that I would go with the alternative. So if I see an extreme value that is on the left-hand side of the x-axis, then I will go with the alternative hypothesis. Okay, so here I draw the curve. And, you know, I generated this by computer, so you don't see me doing it by hand. But I drew the curve, pretend I did it by hand, and then I shaded extreme value on the left. Now you'll notice I haven't actually set what the actual value is. I just kind of scribbled it in just so that I have that thing to remind me, you know, how I'm going to make a decision. Okay. When I get my test statistic, if I see an extreme value far to the left, I will reject the null hypothesis in favor of the alternative. All right, so now I need to decide what is my type 1 error risk tolerance at this point, because now I need to figure out what is the cutoff for this shaded region. Okay, well, typically we're going to go with a small value for this, and these are some common values. By far the most common is 0.05. That is just so common that if you don't know, just go 0.05. So I'm going to set my risk tolerance equal to 0.05. So that is the likelihood of a type 1 error risk that I am willing to tolerate. All right, so now in real life, at this point, I would go out and I would collect my data. And so let's just say that this is my data. All right. Well, in my test statistic, I'm going to need sample average, I'm going to need sample standard deviation, and I'm going to need the number of observations. So I'm going to get the mean, standard deviation, and the length computed off of this. Now I'm going to get my test statistic. So when I'm doing my test statistic, it's going to be x bar minus the hypothesized value of the population average, that boundary value. Then I divide by the standard deviation from the sample divided by the square root of n. Now, if I knew truly, hypothetically, what the true variance was, I would go ahead and put the population standard deviation in this S spot, but most situations we don't already know. So we'll just proceed as follows. All right, so now here, this is my test statistic, negative 2.6. Okay, so now what I need to do, I need to figure out what is my cutoff for the rejection region. I'm going to use quantiles to do this. All right, so I'm going to use QT for this, since we're using the T distribution to identify the quantile. That's since I'm working with normal distribution using sample standard deviation, I need to use a T distribution. All right, the probability is the tolerance of a type 1 error risk that I have. Now, when I'm finding my rejection region, if my shaded region is on the left, that is a lower tail equals true. If my shaded region is on the right, that's a lower tail equals false. Okay, so I've got my risk tolerance, I've got my degrees of freedom is n-1, and then because my shaded region was on the left, I want lower tail. So on the left, it's the lower value, the lesser value is on the x-axis. So here's my cutoff. Okay, so if I see my test statistic is more extreme and to the left of this, I'm going to reject the null hypothesis. All right, so at this point, since I already know what this value is, I know what this value is, I know I'm going to reject the null hypothesis, but let's just keep on going. Now I'm going to compare my test statistic to the cutoff. If my test statistic is more extreme than the cutoff, then I reject the null in favor of the alternative. If the test statistic is not more extreme than the cutoff, then I fail to reject the null hypothesis. Okay, so here is my cutoff. Here is my test statistic. I can see that it is in the shade region. It's more extreme in that direction than my cutoff. Therefore, I reject the null hypothesis. Now, something that I want to point out here, extreme values can go both ways. They can go far to the left, far to the right. If I saw something far to the right, that would be strong evidence for the null being correct, but I'm seeing something far to the left. So it's important to shade this because it helps me remember which side is giving me the result I'm actually looking for. Now I'm going to state the conclusion of my hypothesis test. Okay, so I conclude that I have strong data against the null hypothesis. Therefore, I conclude that the null hypothesis is not the way to go. I reject the null hypothesis in favor of the alternative. Okay? Now, next thing I'm going to do is I'm going to state my conclusion in plain language. So it looks statistically, it looks like the population average is less than 0, is how I would word this. Now, we can also use R to compute most of this pretty fast for us. All right, so our parameters for the T.test is X is our data. The alternative corresponds to the alternative hypothesis. Our options are two-sided, less, or greater. For this one, it is less because the shaded region is on the left. And then confidence level is 1 minus my type 1 error risk tolerance. And then I get a bunch of stuff that comes out. All right, so T is the test statistic, DF is the degrees of freedom, the p-value is the area of the shaded region. A shaded region with the cutoff being the test statistic. And the confidence interval gives us a range of plausible population averages. And then the sample estimate gives us the point-wise estimate off of that. And so when I pass these, I give my sample, I say which direction I want to go in, I say the hypothesized value, that boundary value, and then 1 minus my risk tolerance. So now we have -3 and 9. So -3 is my test statistic. My degrees of freedom is 9. My p-value is 0.01. It's pretty small. And we get 95% confidence interval. So here, there's a one-sided test, so it only cuts off the real line on one side. And here's my mean of X. Now, something about this, if I go back up, I have -2.6 here. And here I have -3. That's because of rounding, because I told it to round stuff off. I did that as an option. So if you notice that there's a little bit of a difference, it's because of rounding to the whole digit, because of how I set the parameters for displaying. All right, so in real life, we're going to be using the t-test function to compute this for us. But the interpretation, you want to go through the same process, even though it crunches it out for you. All right, so now let's do a one-sided t-test. The alternative is on the right this time. Okay, so once again, we believe our data is coming from a normal distribution, and we want to run a hypothesis test concerning the population average. I'm using the sample average, the sample data, to draw an inference about the population average. All right, so the null hypothesis is that mu is less than or equal to 0. The alternative is mu is greater than 0. If I see strong evidence for the alternative, I go with the alternative. Otherwise, I go with the null. It takes strong evidence to go with the null or to go with the alternative hypothesis. Now I identify the boundary distribution. This is the one we will use for testing. So here, I notice that less than or equal to 0, greater than 0. 0 is my boundary value. Therefore, I'm going to set mu equals 0 to establish my boundary distribution. And if I'm working with the normal distribution and I don't know the variance, I'm going to use the t-distribution. My opinion is that if you're working with normal data for this problem, for population averages, you should just use t-distribution regardless. All right, so now go ahead and draw the distribution. I'll shade the region that goes with the alternative. Do this by hand. All right, so I know it's a bell curve, so I go through, I draw a bell curve. I look up at my alternative hypothesis. The alternative is going to the right. I'm going to shade a region on the right. So shade a little bit over there. All right, so if I see an extreme value that is positive and on the right-hand side of the real number line, then I will go with the alternative. If I don't see that, if I see something negative or if I see weak evidence, for the alternative, then I'm going to go with the null hypothesis. One thing that you'll notice how much of this curve is not in the rejection region. This area corresponds to how prone we are in going with the null hypothesis. I need to establish my type 1 error risk tolerance, and I'm going to go with 0.05 once again. I collect my data. I get the mean, standard deviation, and I get the length in, and I get my test statistic. So remember, it's going to be X bar minus the hypothesized value for the population average, which is the boundary for us, then standard deviation and divide by square root of n on the bottom of the fraction. All right, so in this situation, my test statistic is 1.1. Okay, now I need to find the cutoff value of my rejection region. All right, I need to find where was that cutoff for the shaded region I drew a moment ago. If I want a region on the left, I want lower tail equals true. If I want a region on the right, I put lower tail equals false, and we're using the quantile function for t. I put in my type 1 error risk tolerance, put my degrees of freedom, and my lower tail right there. So here I want on the right, therefore the lower tail goes on the right. And here is my cutoff, 1.8. Okay. So let's compare the test statistic to the cutoff. If your test statistic is more extreme than your cutoff, then you reject the null hypothesis in favor of the alternative. If the test statistic is not more extreme, remember that you don't. Okay, so here I can see that my test statistic is not more extreme than my cutoff. Therefore, I fail to reject the null hypothesis. I'm going to state my conclusion in terms of hypothesis testing. So I failed to reject the null hypothesis. And then I state it in regular plain language. Statistically, it looks like the population average is less than or equal to 0. And now for the t-test in R, it's the same thing as what we did before, but I put the alternative as greater. And here we get our results. So t is rounded off to 1 for our test statistic. Degrees of freedom is 14 because we have 15 data points. That's the p-value we get. That is the area under the curve where the boundary is the test statistic. And we get a 95% confidence interval. Now notice it's a one-sided test, therefore it's a one-sided confidence interval. And here's our point estimate.